Assalamu alaikum. Welcome to the series of lectures on advanced computer architecture. In our last lecture, we discussed machine exceptions. We said that exception is a situation where the normal flow of execution of instructions is interrupted and the processor needs to attend to some other event. Now, these exceptions could be generated either from within CPU or from outside. We classified and discussed what are different types of the exceptions. Like we said, we could have a program exception, we could have a data access exception, and so on. Finally, we discussed that how a designer or an architect would provide the handling of these exceptions. So for handling the exception, we need to identify the source of interrupt. After we have identified the source of interrupt, we need to save the contents of the registers. And then we also need to tell the processor or CPU that if there are different priorities, a logic should be there that what are the priorities and how these priorities are to be resolved. Then we said that when there is a critical operation being conducted by CPU, no interrupt should be handled. And we could have a situation of whether we can mask or it is a non-maskable interrupt. Today we will continue and see the processing of the exceptions and how all these functions are done, and we will look on the slides and see the processing of the interrupts. Let us see at the following slide for the explanation of this processing. This slide indicates the SRC, our simple RISC computer exception processing mechanism. First of all, we get a request, and this is indicated by interrupt request IREQ. The next step is that the CPU should acknowledge this interrupt, and we define I acknowledge for interrupt acknowledge. After the interrupt acknowledge, we disable the interrupt flag IE, which is a 1-bit register. Then we save the contents of PC into another register IPC, which is a 32-bit register, and it has to be provided in the hardware of SRC in order to handle the exception mechanism. Then we get the information about the source of interrupt, and that is ISRC info. It is in general identified by 16 bits, and we have an II register about interrupt information. That also is a hardware register, which is in this case identified by II as a hardware register. Finally, we load the PC with the interrupt vector IVECT, which is a 32-bit address indicating the location of the interrupt routine. The next slide shows the behavioral RTL for exception processing. The first table just indicates the instructions, and the second column just gives the meaning. The first operation is to check the run and start. So if the processor is not running, it's not run, and a start is initiated, we put run to 1, and if there is a run and not IRQ and IE, says that it is a normal fetch in the absence of an interrupt. We place the contents of PC into IR and increment PC by 4. The second part indicates the interrupt option. Run and IRQ and IE, that means when there is an interrupt, in that case we will have present contents of PC loaded into the register interrupt PC IPC, and II about the information, it's a 16-bit register, would be loaded from ISR info into II. Same time we will load IE with 0. PC would get the vector address, which is a 32-bit address, as IVEC, and IAcknowledge is set to 1. Now till this point, up to the semicolon, under the different conditions, we have concurrent operations. That means which is indicated by a comma. Here a semicolon indicates that the routine for interrupt has been served. Now we put IAcknowledge as 0. So interrupt copies PC into IPC, II is loaded with the information for about the source, and PC is loaded with the new vector address in order to serve the interrupt routine. In order to provide the SRC processor for interrupt handling, we need more instructions into our instruction set. The table shows additional instructions. The first one is SVI, which is with an opcode of 16, meaning that save II and IPC, and the behavioral RTL is given by the contents of II are placed into the register RA, and IPC is placed into register RB. RI is the next instruction, which is restore II and IPC. This is just the opposite of the save interrupt. So therefore the contents which were previously saved in RA are copied into II, and the contents of RB are copied into IPC. The next instruction is EEN with opcode 10, and that is interrupt enable, and this is exception enable. EE is exception enable or interrupt enable with an opcode of 10. The 1-bit flag is set to 1. Then we have EDI, which is exception disable, with opcode 11. So if a previous interrupt is being handled, IE is 0 in that case. So we place 0 into IE. Finally, the return from interrupt is RFI with an opcode 30, and we place the contents of IPC into PC and set the interrupt flag IE to 1. The next table shows the structural RTL for exception processing. In timing step T0, the structural RTL is written as not IRQ and IE, which means a normal operation, and PC would be placed into the address register MAR, and PC after incrementing by 4 would be placed into buffer register C. That's a normal operation when interrupt is not there. The next column shows the case where interrupt is there. So IRQ and IE means that there is an interrupt request and IE is 1. This has not been disabled. With this condition, if this condition is true, then we place the contents of PC to interrupt PC register and the contents of the source about interrupt information into II, and we force the flag IE to 0. The contents of PC are loaded with the vector. In this example, we have an 8-bit vector. We need to just place zeros on the left and right side of these 8 bits, and this is just indicated by 22 replicated zeros concatenated with 8 bits and further concatenated with 2 zeros. I acknowledge is loaded with 1, and after this routine is complete, the interrupt has been loaded, we place back the I acknowledge to 0, which is indicated with a separating semicolon. The other steps T1 and T2 are the normal fetch cycle for the instruction, followed by the instruction execution, and that execution would continue with the contents available in the program counter. Notice that the 2 zeros on the right side of the 8-bit vector would enable us to have a freedom of incrementing these 2 last bits by 4, and therefore no multiplication of the vector by 4 would be required. That would mean that different addresses indicated by these vectors need to be separated by 4, and that would be very easily done by providing the vector address along with these 2 zeros on the right side of the 8-bit vector. The next table shows how to combine the reset and exceptions. We have discussed the machine reset and machine exception. Now the 4 entries in this table just indicate the first one is a normal fetch operation when there is no reset signal and no exception or interrupt, and you can recognize this is just a normal operation with run and not start and not interrupt. That means the signal is 0 as far as interrupt request is concerned. There is no interrupt request. The second entry indicates a soft reset signal indicated by the condition run and the signal reset RST. So RST 1 and run 1 means it is a soft reset, and we place 0 into PC, and IE is also forced to 0, RST is forced to 0. The third entry corresponds to hard reset, which means we have a start signal STRT. In this case, along with the PC, all the registers, 32-bit registers, are forced to the initial value 0. And the last one indicates the interrupt. So it's the most general form where we have the soft reset signal along with interrupt. So this is the structural RTL description for the combination of reset and exception. We have seen now how to have an update for SRC in order to incorporate the interrupt handling. So therefore there are two consequences. As far as hardware is concerned, in the data path we need to add two more registers, and we just called these registers as IPC, which would just copy the contents of PC on interrupt, and II as a register which would identify the source of interrupt, that would be copied into II. So when we have these two registers, we need to connect these registers to retrieve and place the information. That could be done either through the bus or extra connections could be provided for these registers. As far as the software is concerned, we needed additional instructions, and we just saw that there are 5 additional instructions which we extended with 5 different opcodes. So altogether the instruction set of SRC also was modified in order to incorporate the handling and processing of interrupt. Now finally, we also saw that the reset and the interrupt could be combined together and implemented. So as a result, you should be very clear how to write the RTL description for reset and RTL description for interrupt, and combined reset and interrupt for the case of a sample processor. You could do a similar thing with other processors, and as an example, I would suggest that you take the instruction set of Falcon A and try to upgrade it, incorporate the reset option, both hard and soft reset, and at the same time the interrupt handling should be incorporated. And that would be a good exercise and would give you more insight as a designer of a CPU how to incorporate these two aspects, the machine reset and machine exceptions. Now as a designer, we just have looked into the example of SRC, and the fetch execution was the feature of this processor. Now if we want to improve the throughput and we would like to have a better performance, what are other options available with us? Pipelining is a very important concept, and we now just discuss and look what is pipelining, how it could be implemented, and what updates would be required in an example SRC. And these are the features that we need to discuss now. Now the pipelining is defined by different authors in different ways. Now one thing is quite obvious, that the pipelining is done at the implementation level. So therefore, if we have just the available resources, available instruction set, then one instruction would be fetched, executed, and after execution of that instruction, the next instruction is fetched, and so on. Now, if we want to improve the performance, there are physical limits. For example, a clock frequency could not be increased beyond some limit. Now, with the present hardware for a processor, you could add up more hardware and maybe get a better performance, but that also would mean additional cost. Now, the pipelining concept looks into the aspect of what is called the parallelism. So, in the different instructions, there could be some instructions which could be executed simultaneously. So we need to have some overlap between the different instructions in order to get a better throughput. A particular instruction may require same time for execution or even a little bit more. But when different instructions are executed at simultaneously or with the help of some more hardware, then we have more throughput. Now, one thing should be quite clear, that if you define the parallel mode of operation, by definition there are three architectures. You could say single instruction, single data, or multiple instruction, single data, multiple instruction, multiple data, single instruction, multiple data. All these architectures are defined for improving the throughput. However, the pipelining does not fall in any one of these four conventional definitions. We could find an analogy, a very nice analogy for pipelining. There is a simple mechanism where we have an assembly line. So in an assembly line, we define different processes. Just as a general example, suppose in a workshop or in an assembly line, a piece is to be worked and there are three operations to be done. For example, there would be drilling required, there would be polishing required, and some sort of other mechanism of packing, let us say. So if we have just one person, he fetches the piece, he drills. After he has drilled, he would just polish it and then pack it, right? So on the other hand, if we have an assembly, then a number of pieces would come and would pass through each stage. And in each stage, one operation would be done. So at a time, three operations could be done. Actually, it's a queue. It's a queue of drilling, polishing, and packaging. So there would be one person sitting drilling, and a piece comes. If it needs to be drilled, drilling would be done, and that piece would be passed on to the next stage of polishing. If polishing is required, that would be done, and then it would be passed on to the packaging. So the efficiency or overall throughput would improve by this model of what you can call an assembly line. Exactly in the same way, we define in our processor, in our CPU, the total activity could be split up into sub-activities, and we could define the modules, the sub-modules, and a particular instruction would pass on. It would drag through this series link which forms a pipe of the instructions. We can illustrate this concept with the help of a very simple slide which we see now, and we will just see what is the basic concept behind the pipelining. This slide shows, with the help of a simple block diagram, two situations. The upper part shows the concept without using a pipeline, and the lower one with pipeline. Now, we have defined, just for illustration, 5 different processes. First one, fetch instruction. Second, fetch the operands. Third is arithmetic logic unit operation, ALU operation. Fourth is the memory access, and last one is the register write. Now, if there is a normal routine without the pipeline and we want to execute, for example, add the contents of registers R2 and R3 and place the result in R4. With this instruction, at one time, only one of these 5 blocks would be busy and all other four are idle. After add instruction has been executed, then we can just fetch the second instruction and use one of these 5 blocks depending upon which type of instruction is being executed. However, we can improve the throughput if we could issue a new instruction before the previous one has completed its execution. And that's the concept of the pipeline. That means there should be overlapping of instructions. Now just see the lower part of the slide. Now in each stage there is some instruction. For example, in the fetch we have the load, in the second fetch operand we have store, in the third one add, then subtract and shift left. So this would mean that each subsystem or each process which is indicated by just a square block in this case is busy doing something. Now we have assumed at this point of time that if all these instructions are isolated and could be run and executed independently, then at every time some activity is going on in the process, and theoretically, although each instruction when passes through one block to the other, from one process to the other, would have some delay, which is the latency. In this example, it could be a latency of 5 clock cycles if every stage takes 1 clock for execution. But the achievement would be, ideally speaking, if all instructions are independent of each other, the throughput would increase 5 times. So we increase the throughput at the cost of some latency being introduced or some additional delay for each instruction. We illustrate this concept with the help of a very simple program indicated in the slide. There are 5 instructions. The first one is shift right, second subtract, then add, store and load. And we pass these instructions one by one through our model of 5 processes or a pipeline having 5 stages. Now in this slide you just see that we conventionally just take a vertical model. We take the top block as the first one and the bottom one as the last one. So we number top one as 1 and the bottom is 5. If we place it horizontally, then left one would be the first one and rightmost would be the last, which is the 5th. So each instruction enters the first stage, and then on the next clock cycle it moves to the second one, and second instruction is popped into the first stage, so on. Finally, after 5 clocks, the situation is shown, and you see that the load instruction, which was the last instruction in our program, is in the first stage, and the first instruction is in the 5th stage, that is the shift instruction is in the 5th stage. Now there are a couple of observations you could make out of it. At this point, which is indicating the 5th clock, the subtract instruction is present in the module which corresponds to memory access. However, there is no memory access required in the subtract instruction. So therefore, nothing would be done with this instruction. That means this module would not perform anything. In our conventional example of drilling and polishing, that would mean that if no polishing was required for a particular piece, that piece would stay idle and would be passed on to the next stage without any operation on that particular stage. Similarly, on the next clock cycle, the subtract instruction would be dragged into the second stage, and that would mean that it would not contribute to additional throughput in this example. Now similarly, we could have a situation where the second instruction might require the output from the first instruction. So therefore, the execution of the second instruction could not be done unless the results are available from the previous instruction. And that also would impede the throughput, and therefore, ideally speaking, the throughput would not be simply a multiple of the number of stages. It could be, in the worst case, no improvement, and in the best case, multiplied by the number of stages. Now again, it's very important that you realize and see this example. We have 5 stages in the pipeline. Function of each stage is indicated clearly for this example: fetch instruction, fetch operand, ALU operation, memory access, and register write. And the 5 instructions being executed are indicated for a typical position of the clock. Alternately, we could also represent it with reference to the clock cycles as indicated in this slide. Now, for one cycle of the clock, we have one activity. So, just for simplicity, we have assumed that the operation in each of these 5 stages is completed in one clock cycle. So, for example, in this figure, we have in cycle 1, I fetch. In the second one, we have register and decoding. And then in the third cycle, we have the execution, and then the memory access, and the last one is the register write. So, just for the sake of simple explanation, we have shown horizontally along with the clock each activity being completed in just one cycle. This is for simple illustration of the pipeline concept. The concept of pipeline is not new. It's pretty old and was developed in 60s. However, with the development of a risk philosophy, the instructions were reduced, were simple, and the concurrence of different instructions or parallelism in instructions could be exploited, and then implementation of pipeline was done after the development of the risk philosophy or risk architecture. Let us now look at an important feature, and that is the throughput defined in terms of bandwidth and the delay defined in terms of the latency. Now, throughput or bandwidth we could measure in terms of MIPS or mega instructions per second, and the latency you could define in terms of the delay for one instruction, or that would mean the time required for executing one particular instruction. Take a very simple example. If we are not using a pipeline, and suppose one instruction at a time is fetched and executed, and one instruction requires 3 clock cycles for execution, right? So therefore, if the clock frequency is 100 megahertz, what would be the bandwidth? So in terms of MIPS, we could define the bandwidth as 100 divided by 3, because each instruction requires 3 clock cycles and one instruction is being executed at a time. So therefore, the throughput for non-piped situation would be, or the architecture without pipeline would be 33 MIPS, 33 mega instructions per second. Let us now consider that we introduce a 5-stage pipeline, as we discussed in the last example, with some 5 arbitrary blocks or 5 different activities. So each instruction would be fed into this pipe and would come out of the pipe after 5 clocks. So therefore, the latency in this case has increased from 3 clocks, which corresponds to 30 nanoseconds, to, in pipe situation or using a pipeline, it would be 5 clocks, meaning that 50 nanoseconds would be latency. On the other hand, what would be the throughput? What would be the bandwidth, right? Each instruction is being executed in 1 clock cycle. So therefore, the throughput is 100 mega instructions per second. So it is 100 MIPS. So in general, this is true, and we could say that we achieve throughput at the cost of latency. So latency would increase, but throughput would increase, and at the same time the delay would increase. So in the form of latency, we have a higher figure in delay. So longer the delay line, longer would be the latency, higher would be the latency, but throughput would depend on, ideally speaking, we have assumed that each block in our example of 5-stage pipeline requires 1 clock, but this may not practically be the situation. Secondly, it's extremely important to see, we have made certain assumptions. We just said that different instructions are independent of each other, but practically it would not be so. There are dependencies among the instructions, and that would give a reduced throughput. So therefore, we need to overcome and see how these dependencies would be resolved. So what is dependency and how it would be resolved? Let us see with the help of a slide. Dependency among instructions means that some instructions depend on the completion of other instructions in the pipeline. As an example, the slide shows 2 instructions, an add and a subtract instruction going through our 5-stage pipeline. Now, add is the instruction where 2 registers R1 and R2 would be added and the result would be placed in R3. However, this R3, which is a destination register for add instruction, is now an operand for subtract instruction. So unless add has been executed, the subtract could not be executed, and there is a dependency among add and subtract instruction. So in the figure, we just see that the add instruction, as an example, is in cycle or stage 3, and the subtract instruction is in stage 2. Now, when add is executed, after that the results would be provided to a subtract instruction which could not be completed. So therefore, subtract would wait till add is completed and the result is available in register R3. How do we overcome the dependency among different instructions, as in the example of add and subtract? There could be different possibilities, and there are 2 major options available to the architect. We could use the concept of stall. In that case, where the dependency is there, we introduce additional no-op operations for the processor, or at different stages we could use the waiting process implemented by no-op till that particular instruction gets the data from a previous instruction. That would mean a decrease in the throughput, but the problem of dependency would be resolved. The second option could be that of data forwarding. So we could have intermediate buffers and store the results from one instruction and pass on these results from intermediate buffers to the instructions which require this particular data. That would be primarily a simple concept or simple explanation of data forwarding. Now the question is it only the dependence among the instructions that would cause the no-op or delay and reduction in throughput, or could there be other situations? Well, there are other situations also where there is a dependence. One example could be when we are interacting with the memory. From the memory, the data might take more time to be fed into the pipeline, and that would also give us a delay in the form of load. So that would be called a load delay. Now the second situation could be in situations where we have branch instructions. For the branch instruction also, a delay is involved when the process is completed and the program counter is uploaded, is loaded with the address where the execution control is to be given. Additional waiting time would be required, and these dependency on memory and on the branch situation would also result in the throughput being decreased from a pipeline. The idea of branch and load delay is illustrated with the help of an example in the given slide. The first part of the program shows branch on 0. So the instruction is branch on 0 R2, R3. That means depending on the contents of register R3, we branch to the address indicated by register R2. Immediately following the branch instruction, we have add instruction, add R6, R7, R8. Now, before the condition is evaluated, the add instruction would be executed anyway. It would always be executed. Now the next instruction, store R6 address 1, would be done only if the contents of R2 are not 0. So this would mean that when we come to the store instruction, the contents of R6 would have been updated by the add instruction, and that might give data inconsistency. To avoid this, we need to put in and stuff no-op between the branch and the add instructions so that the add is not executed and branch is first evaluated. Depending upon the condition given in the branch, we may or may not execute the add instruction. Similarly, the next instruction is load delay. Load R2 from a given address, and following that we have address add instruction, adding the two registers R1 and R2 and placing in R5. Now R2 would be changed by this add instruction. So again, the load would not have been completed when we execute add, and again the contents of R2 may not be the valid contents as available after the load instruction. So in this case also we need to incorporate the stall situation or add no op instructions in between load and add instructions. Now through better programming practices, we could rearrange the instructions in such a way that this situation does not arise. But anyway, if such a situation arises, we need to have a stall situation and just make sure that through a branch or through a delayed availability of data from memory, other instructions are not affected. Let us now look into some of the important requirements for designing a pipeline or a pipeline architecture. We will illustrate these ideas later on with our example of SRC. First of all, the instruction set should be consistent. This means that to a programmer, it really doesn't matter or doesn't mean, or there's no way to find out whether there is a pipeline or not in the processor. So this would mean that the instruction set to the programmer is the same, and therefore the behavioral RTL description would not be affected. However, the programmer would just feel the effect of pipeline in terms of performance, in terms of throughput. So therefore, his program with the same number of instructions would run faster. Now, when we are using the pipeline, the implementation would change. So therefore, it is important to note that although the behavioral RTL description has not changed, but we do not have the same structural RTL description. So since implementation has changed, the structural RTL implementation would definitely change, and we need to note that point. Now the second design requirement is that for an architect without the pipeline, we have a common memory. That means the same memory has the instructions and the data, and that is the usual phenomenon concept. However, for the pipelined architecture, this would cause problems, and we would not be able to easily interact with the memory, and therefore some sort of modification is required, and that can be done more efficiently if we use Harvard architecture, meaning that we do have a separate memory for address, for fetching the instructions, and for the data. Now, it doesn't mean that physically we need to have two physical memories. It could be the same memory organized into two different caches. We have one cache memory for the instructions and the other one for data. So therefore, this is also an important design concept which goes into an efficient design of a pipeline. Now, then we need to have another aspect, and that is the reading and writing from the registers. So the registers might need multi-ports. So as we saw in the case of 3-bus implementation, that we had one input port and two output ports for each register. So with the pipeline, we need to have an option of simultaneous reading or writing from a register. So this could be done in different ways, and we could have direct connections along with the buses or without the buses among different registers to make the transfer efficient. So therefore, the pipeline would not need to wait for just lack of connections in the architecture. So therefore, along with the buses, either we could have a better bus implementation, or we could provide additional connections into our pipeline architecture so that we have efficient utilization and a better throughput from our pipelined architecture. We'll see these concepts in more detail with the help of examples for our SRC processor. There are two other design parameters for the pipeline. One is related with provision of intermediate buffers. Since in our example we have 5 stages and the number of stages could vary depending upon the processes or the activities. But nevertheless, to store the intermediate results from one stage to the other one, we need to have the buffers, and that would be an implication required for the hardware. And finally, for ALU unit, arithmetic logic unit, we would like to have operations in one clock cycle. You remember from one of the earlier lectures, with the help of barrel shifter, we could just have the shift operation just in one go or in one clock cycle. So the faster hardware provision in ALU would be required for implementation, for a better implementation of ALU. Now, next time we will be discussing the implementation of pipeline or pipelining concept in our design with the help of SRC or example processor. Till next time, Allah Hafiz.